welcome everyone to our Thursday seminar. Today we have with us Dr. Yanga Bavuma, who's visiting us this week from UCT. So Yanga did undergraduate studies, as I was told, from Rhodes before moving to UCT, and he completed his PhD under the supervision of Prof. Francesco Russo. He currently works in topology, topological groups, and now he's dabbling in graph theory as well, as you can type a lot of this talk. So we look forward to hearing about integral Cayley graphs, polygroups. Thanks, Yanga.
Yes, as you guys said, the university is very busy. As you can see, we're talking about an infinite family of integral Cayley graphs or polygroups. Now, the integral in integral Cayley graphs stands for, we'll go into it, but it's spectra, and the spectra of the Cayley graph, which are literally eigenvalues of matrices that you associate with these Cayley graphs. They are just integers, so the values are integers, and that's why you got the integral in there. So I'll go over quickly what Cayley graphs are, and these polygroups. These polygroups are an extension of a classical group in physics called the Pauli group, which it can be used to in quantum information theory to do some quantum computing coding and coding corrections, and there's an infinite recursive way of defining these polygroups as we go forward. So today is the May 12th. If any of you were mistaken, thinking it was the 29th, it turns out it's May 12th. Should have fixed that. Yeah, so essentially, yeah, I've got this abstract, and this abstract, if I leave the slides with a screen, you'll be able to go through, and it essentially just explains that this was the continuation of my PhD thesis project, and then goes into the motivation for studying it in terms of spectral graph theory. So the contents are, first I'm going to give the background, which is basically my thesis that I did in my PhD. Actually, this is a paper I wrote as a short note on this work that I did in my thesis. The first part of it will be giving this background. And this background involves me defining what the Pauli group is, then the central product, which is essentially the main structure that we are currently interested in when it comes to talking about this Pauli group, these extended Pauli groups that we'll be defining in a recursive fashion. Then I will briefly mention what a Riemannian manifold is, because it ties into the main theorems of the background paper, and the fundamental group for those who are unfamiliar. Then the subsequent inquiry that led into this main paper, which is the main part of the talk, and this is a paper that I published in the Journal of Algebra with Professor Dono and Professor D'Angeli and Professor Rousseau. So this was joint work. I'll just introduce what I mean by graphs, then talk briefly about graph products, more specifically the direct products, and then introduce how the central product can be taken. The central product from the previous talk, from the previous section, will be elaborated and defined by us in the graph products sense. And we show that everything kind of works out in the isomorphisms you expect to exist. Then I will introduce adjacency matrix in the spectra, which is what the talk is mainly about, spectral graph theory. Then this main theorem, which is that the central product of Cayley graphs is the Cayley graph of the central product. So it was nice to have this this invariance property when it came to talking about central products, and you'll see why. And then we'll look at the case of generalized polygroups and how to calculate their spectra, which was the main point of the paper, how to calculate the main spectra of the generalized polygroups. And then I'll just go into the main theorems from the paper. This talk will be too long for me to go into any specific groups, so I will leave references at the end if you want to go to the groups of the papers. but I'll just be going over the theorems and explaining what the theorems are. So the Pauli group, what we talk about when we talk about the Pauli group, we denote it P1 because it's technically the first edition of the Pauli group. When you are generalizing it in this specific case, we're going to be generalizing it in. And this is a group, a finite group of order 16, and it's a group that's generated by three matrices. These are called the Pauli matrices, named after the physicist Wolfgang Pauli. Yeah, so these are the three matrices. These obviously is just a representation of the Pauli group in matrices where the field that they write over is the complex field. These are very important. They help with in like I said, quantum information theory. And he came up with these matrices to take into account the spin of I think it was an electron in an electromagnetic field in the three directions of X, Y, and Z. And one can check that they satisfy these properties, which allows us to be able to define this is along with these three generators, we can have these relations, and we'll have our group presentation for the Pauli group. And what the Pauli group really looks like is just plus minus I. I is the identity matrix, and then this little I with the big I. The little I is just the imaginary coefficient, and so plus minus the identity I times the identity, and then plus minus X, IX, Y, and so on. This gives us the entire group. So it's a group of order 16. It's a finite group. These matrices are also very cool in that the real span of them can span all the Hermitian matrices, which are very important in the quantum mechanics when you're dealing with looking at observables. You use Hermitian matrices when you're talking about finite operators to be able to look at observables. So they give you real spectra or real eigenvalues as constants. So next, we need the notion of a central product. This is a technical definition, but the idea here is that when we're taking a central product, we take two groups, and then we take their direct product, and then we identify the subgroups of each of their centers. So we'll have a group, let's say a group H and a group K will form take some subgroup that's isomorphic in their centers, form a direct product, and then identify their centers. And that's what we mean by a central product. So another nice thing that comes with having a central product is that if you extend our H to H plus 1 and call it H bar, then we can actually find an epimorphism from D is just H cross K, so one H cross K onto G, which is our central product. So basically, this says that our central product is actually a quotient of the direct product, which is what you'd expect, given the fact that we identify their centers. So yes, that's basically the same thing I just said. So finding a Riemannian structure for us was not so much like technically into like talking about differential manifolds. We just needed a structure that essentially meant finding we're able to define a Riemannian metric on whatever manifold or topological of which we were dealing. And so Riemannian structures are really helpful when we're dealing with quantum models because they help with simplifying a lot of quantization processes. And so we wanted to find, which is a classical thing in algebraic topology, which is my first love. And I'm doing a whole lot of stuff working in quantum mechanics, spectral graph theory, but I like algebraic topology. And in algebraic topology, it's a classical notion or classical end of for us to be able to find nice spaces with nice properties. So what we did for my paper was essentially find a compact Riemannian manifold of which you can take a fundamental group of it and then find the Pauli group, at least as a quotient. And so it was important for us to have this Riemannian structure so that when we're doing any applications with quantum mechanics, it will simplify these quantization processes. Just like you can find in papers by Chikotko and Romanenko, and also quantum mechanics on finite, on quantum mechanics on spaces that have finite fundamental groups are really helpful in this paper I can send you, are really helpful in, like I said, simplifying certain quantization processes. So yeah, such structures can be found in the context of Lie groups, or those interested in Lie theory. And then next, talk about the fundamental group. Well, the idea of the fundamental group, this is again a technical notion, but the idea of a fundamental group is that it's the way of counting and keeping track of the complexity of the loops that you can find in a space. This is the first fundamental group, and there's various ways of defining it using, let's say, I, but you have to identify the ends. But I like this definition where you look at S1, you take a function that goes from S1 to X that is fixed at some point 1. And this point doesn't really matter where it is, it's a circle, but the point is that you fix that and you look for the equivalence classes of all loops that you can get that will be fixed at a certain point and then can be continuously deformed into one another. But this is just another fancy way of just trying to find a way of how complex the loops that you can find in any specific spaces. So this is a fundamental, and this was when I first saw this, it blew my mind. This was my first real interaction, I guess, with mathematics. And this also, I guess, happens to be, I think, one of the main ways in which category theory was started, by having these sorts of processes where you can start off with a topological space and then come up with the group of this topological space, but not only be able to just have a random group on it, but this group will give you information about the topological space itself and having moved from a completely different context. And here, there's a way of defining the product of the operation between the groups that is consistent, or the elements that is consistent. And also the neutral element is just a constant path. And also you have a reverse loops that just go in the opposite direction. And all of these can be shown to be consistent for the fundamental. So as I said, it was remarkable because, you know, you could find algebraic properties from topological spaces to this fundamental, which blew my mind. And that's where my love for mathematics and algebraic topology started off. So why the central product? Well, the Pauli group itself can be written as a central product. It's actually a central product of the dihedral group of order 8. So I use D8 to denote the dihedral group of order 8. So it's actually the dihedral group of a square, but it has order 8. And so we use D8 just so we could consistent with the notation of the quaternion group, also order 8. And just showing that these two groups are actually very similar in terms of their structure. And you will actually see even their structure in graphs makes them very similar. And so the Pauli group can be written as the central product of the cyclic group of order 4 and the dihedral group of a square, or it can be written as the cyclic group of order 4 and the quaternion group of order 8. That is, you have these two ways of representing the Pauli group. So the first Pauli group. I'm not doing well enough. Okay. So we found as a theorem that if you have a group G that can be written as a central product, of its finite groups H and K, and you know that H and K satisfy the following conditions. That first of all, both H and K contain no subgroups that are isomorphic to ZP cross ZP, where P is prime. So both H and K cannot contain these subgroups. And also that both H and K contain at most one element of order 2. Then I can guarantee you a Riemannian manifold X of dimension 3. It's actually also compact, as we mentioned, and a surjective homomorphism from the fundamental group of that Riemannian manifold onto G. And Q8 with the quaternion group of order 8 and Z4 satisfy these two conditions. However, D8 does not. It actually contains more than one element of order 2. And so it does not contain this, it does not fulfill this set of, I think, conditions. And so it doesn't work for us. So we're not able to guarantee this nice manifold that we would like to have for the theorem to work. And this is because Q8 and Z4, they act very well, and this is in the context of group actions, which I will not be defining, but they act very well on S3, which is the three-dimensional sphere, and this action allowed us to be able to define orbit spaces that maintain the Riemannian structure and also maintain the manifold structure of the resulting of S3. So S3 has a Riemannian structure and S3 has a manifold structure. And so taking Q8 and Z4 and acting on it and then forming orbit spaces, the resulting orbit spaces themselves have these structures from S3 that are very nice. The fact that they're compact and a Riemannian and that it's a manifold. So in fact, corollary of that previous theorem just says that you can have these two path-connected, compact path-connected orbit spaces. U, which is L3 Q8, so it's the orbit space of L3 under the action of Q8, and then L3 under the action Z4, and U hash V is the wedge sum. Now, the wedge sum is essentially you take any two manifolds, and in order to preserve the manifold structure, we cut holes in n-dimensional holes in an n-dimensional manifold, n-dimensional holes, actually n-1 dimensional holes, and then stick them together along the borders. This way that you don't have some sort of way of, let's say if you use a wedge sum and you connect them by a point, then you break that manifold structure at that specific point. So you need to cut holes and then stick them along the boundaries. So you stick in the two manifolds along the boundaries, and that allows you to be able to preserve the manifold structure. And so that's what this hash is there for. And so having that U hash V, the dimension of it gets maintained, so it's still dimension 3, and the fundamental group, this should be fundamental group 1 of the P1 is isomorphic to some quotient of this fundamental of the space U hash V. So yeah, as I was saying, the nice thing about this result is that S3 is one of only two spheres that can have a group structure on it, the other one being S1. And so we have a nice topological group, and also, but we were more interested in it as a topological space, but it's a topological group, so you have a nice topological group that you be able to do all this work on and find this nice properties that are getting maintained from it. And so you can think about doing quantum mechanics on it as some sort of leap. So it was nice that we were able to do this with F3. So that theorem that we came up with the Riemannian manifold, although the topological nature of the Riemannian manifold itself did not lead to any, I think we hadn't looked at how to do quantum mechanics on it, but the algebra that came out of us giving that proof was able to you were able to use the algebra of giving that proof to show that in some particular pseudo-fermionic system. Now, in quantum mechanics, you have generally two kinds of subatomic particles that you can have, fermions and bosons. And fermions are the kind of particles that carry matter, so in the usual way that we think of matter. And bosons are force-carrying particles. So there are specific ways of writing these fermions and certain relations that they have to obey. And if you relax some of those relations, you get what are called pseudo-fermions, which turn out to have practical applications. And so we looked at a system or two systems involving pseudo-fermions, where they had a group of symmetry on it, P1 and Q8. So these were two systems, F and P, and they had two groups of symmetry, P1 and Q8. And what I mean by group of symmetries, we're talking about the operators on that system that commute with the Hamiltonian of the system. So the Hamiltonian is the operator that governs the energy of the system. And so if you have a group of symmetries on it, you're talking about, in this specific case, the group that acts on the commutes with the Hamiltonian. And so we're able to find two systems, F and T. One has a group of symmetries on it, P1, so order 16, and then the other one has Q8, so order 8, yet they have the same Hamiltonian. And in a way, these two systems are essentially describing the same system, except one has a smaller group of symmetries that's on it than the other one. And somehow, therefore, was a lot. The account of Z4 in P1 acted as sort of they were adding no real dynamics into the equation, or no real dynamics into the system. And yes,
how's the Hamiltonian defined here?
I don't have it in the talk, but it's in the paper.
So this is the Hamiltonian in terms of how we.
No.
I talk about the pseudo-fermions.
Yeah.
Fermion Hamiltonian has Pauli matrices explicitly there. So which is the Hamiltonian here?
So this is the Hamiltonian of the specific systems. We came up with first. We had to come up with a couple of operators that we worked on it, and then we formed the Hamiltonian on its own. But the Hamiltonian itself, it's commuting with the particle, but it's not formed from the particle.
Okay.
Yeah.
So the degrees of freedom are something else. This time the dynamic is S and T.
So
I just wanted to understand what are the degrees of freedom that go into that. Hamiltonian will have a specific space on which it generates dynamical evolution. What is that space? Are the momenta and the.
So this part was mostly brought to us by Guerrero, who was working on the quantum mechanics side of Bavuma, and what he did, he was looking at a specific system where it was a simple system, some sort of harmonic oscillator, system. And then, yeah, that makes sense, right? Okay, yeah.
Instead of what happens to D
The yeah.
It's like a D is. Can you make the same statement? Replacing Q by a D.
So that is something that we ended up not checking because if you remember the space that we came up with, we were able to find the fundamental group of it because of the fact that Q8 acts on the S3, right? And so the algebraic expression that we got as a result of looking at that specific system is what led us to coming up with this theorem. So because D8 was not able to fit and act on the S3 the way that we wanted to do it, there was no way of algebraically expressing D8 in this sort of way that was able to give us these operators that ultimately led us to this theorem. Yeah, there was no way of checking. Yeah. 3 minutes. Okay, try to do this. So conjectured. So we conjectured that this central product has got to be in some way, not got to be, but we conjectured that maybe in some way we could use the central product and the fact that we have Q8 to simplify systems in the same way that we simplify this sort of system. And the fact that Q8 acts so well on S8 would be one of the reasons why this allowed us to be able to come up with this simplifying this simple system going from Q1 to Q8. And so this was something we were supposed to look into. But I was just intrigued by this geometric investigation and wondered if any other maybe sort of combinatorial properties of the Pauli group could be simplified some other kind of system. And so what I wanted to do was work on the Cayley graphs and see if we could use D8 and Z4 and simplify the spectra that you could get in much in the same way that you did with the previous theorem. I wanted to see if we could do this with looking at spectra because we've been helping part of this ISAM project, the Italian Celebrity Research Project, and we've been working a lot with spectral graph theory. And so part of my interest was like, okay, we're able to do this for quantum mechanical systems, at least theoretically. And now I want to see if the same thing could happen with spectral graph theory. And so I wanted to look at the Cayley graph of Q8 on 2 generators, which look like this. And Cayley graph of Z4 with 1 generator, which looks like this. And I wanted to see if there was a way in which we could simplify maybe the spectra of calculating the additional or the general Pauli groups using Q8 and knowing that Q8 has this way of acting on a sphere and maybe it just simplifies things better for us. So that was the motivation for the work that we ended up doing. And so this is the first part of the next session. We have I have to talk about what an undirected graph is. An undirected graph, I'm sure we know, is just a pair where you have vertices and edges. And the edges are just a set that contain 2 elements of the vertices on them. So they're not, there's no direction. Essentially, that's what it means by being a simple undirected graph. And in fact, we're going to be dealing with simple graphs. These are graphs that don't have edges on self-referential edges on a vertex. So a vertex cannot have an edge around itself. It's just a simple undirected graph that we'll be dealing with. This is from me writing earlier. I don't know, it's too late to get rid of this, but I send it to you. Yeah. But anyways, if you let G be a finite group with a generating set, this is just to define what a Cayley graph is. Then the Cayley graph of that group is just a simple graph where the vertex set of that graph is G. So the elements of the graph form all the vertices, and then you're able to get an edge between any two elements of the vertices if the generating set that you chose allows you to be able to go from one element to the next element. And so when you're talking about a Cayley graph, you need to have the group itself and you need to have a generating set S. And so here I wrote, if you have two vertices, X and Y, then you only have an edge if X and S, where S comes from the generating set, X and times S gives you Y. That's the only time you have an edge. Or if X S inverse gives you Y, then you also have an edge. In order to avoid loops, then we have to forbid the presence of the identity element being in S. So note that every Cayley graph is going to be connected because you can connect any element through some sort of path. So this graph will be connected always. And an example would be this is the Cayley graph of Q8, which I showed you earlier. So it has two generators, I and J. So if you remember how the quaternion group works, if you start at Y and use times by I, you're going to go to this vertex. And if you times by I inverse, you go to this vertex. So this vertex is I inverse. If you multiply the two of them, they're going to give you I. Then the other one is J. J will send you to that J, and then J inverse will send you there. And those are the only two. So we have four edges coming from each point. So this is a regular graph. You've got four edges coming from each and every single point. Why? Because you have I as an element of the generating set, as well as I inverse, and filling J and J inverse. Now, this is D8, and as you can see, it looks very similar to it looks very similar to Q8, and it only has three coming from it. It only has three labels coming from it. And why is that? Well, it turns out that R is equal to its own inverse. And so if you start here and you go R, you will go up in the stage 4. But if you start here and you go R inverse, which will give you R, it's the same thing as going up to 4. But D will maybe take you down here, and then D inverse will take you to that side. And so each of these vertices only has three edges to them. So the three regular graph. That was basically what I explained. And then here we have the K4, Z4, and we only have one generator. But that generator has an inverse that is not equal to itself, and so each vertex only has two edges on it. So the two regular graph. So talking about graph products, when you have two finite graphs, you are able to define basically a direct product of graphs. And this direct product of graphs basically works in the same way on the underlying set. You take your underlying vertex set and then you direct product it with the vertex set of the other group. But then here you have an edge between two points. If, remember now, a point is a new vertex in this graph product, it's going to have a vertex that's VG cross VG2, which means it's going to be it's going to have two components to it. Now you have an edge if the first vertex of the first component are equal, and then the second components are adjacent to each other, or the other way around, where the first components are adjacent to each other and then the second component is equal to each other. And that's how you have an edge between any two of your resulting graph. So it follows that if you have this G1 it's going to be a regular graph, and it's a regular, if G1 is a regular graph of T1 on N1 vertices, and G2 is a regular graph, which is what happens with the Cayley graph of degree D2 on N2 vertices, then this is the notation that we give for the direct product of these graphs. Then the regular graph is going to have degree D1 plus D2 and on N1 times N2 vertices, which you'd expect. That's what the cardinality of this set is going to be, N1 times N2. Nice property we have is that G1 cross G2 and G2 plus G1 are isomorphic, so there's no conflict in the way that we define this this graph product, and everything works out nicely, which turns out to be the case when we're talking about the central products as well. So just an example of what this graph product looks like. Sorry, if you take we call this K2, just has two edges and then two vertices and then one edge between the two. If you take that and the direct product with it in terms of the graph product, it's the same as taking this and then putting it on that side and putting another one on that side. And because there's an edge between the two, you're going to have an edge between those two, which is why we end up getting our Cayley product, our Cayley graph of Z4 on one generator as being the direct product of K2 times K2. And then here, our D8 can be seen as taking Cayley of Z4 and doing a graph product with it with K2. Here you can see if you take this and you put it on the edge here, you put it on the edge, put it on the edge here, and you put it on the edge, then because there's these edges that are connecting these two, you would connect those two edges, and then because of the edge connecting these two, you connect these two edges, and so on, and then what you have is this Cayley D8. Now, we found that this Cayley D8 has such a simple structure to it compared to the Q8, and then as I was doing a lot of calculations on gap, trying to find and solve the spectra, it became a lot easier to find the spectra of D8, and it became, in practice, a lot easier to do the calculations because of this simplifying structure, because there's already theorems on how to calculate spectra of graph products like this, or direct graph products. And when I talk about spectra, what I'm talking about is that when you have a graph, you can identify, you can associate with it several matrices. And one of those matrices is the adjacency matrix, which is the only one I'm going to be talking about in this talk. There's the Laplace matrix, impedance matrix, distance matrix, a whole bunch of matrices you can identify with it. And many generalizations of them. So the study of eigenvalues and eigenvectors of these matrices, together with the number of its applications, is like the main objective of spectral graph theory, which is what we were trying to find applications. So we will focus on the adjacency matrix, and the adjacency matrix here involved where you have a matrix. It's going to be n by n, number of matrices, the number of vertices times the number. So you will number each column using vertices and each row using vertices, and then whenever you have an edge between a vertex, you put 1, and if you don't have an edge, it's 0. And each, since we're dealing with simple graph, along the diagonal, you'll have zeros because there's no self-referential graph in terms of the edges. And the adjacency matrix is symmetric by definition, because if something is connected to, if U is connected to V, then V is connected to U. So it becomes symmetric, and so eigenvalues are real and constitute the so-called adjacency spectrum, or we just call it spectrum for short. And so when we are associating spectrum with the graph, we'll look at the graph, and where there isn't confusion, we're just going to say the spectrum of that graph, but what we mean is actually the spectrum of the adjacency matrix. So, example of an adjacency matrix of Cayley Q8 with the two generators. And as you can see, they're symmetric, and each is four regular. There's four edges, whether you go along each row or each column. And then here, these are the spectra. These are the eigenvalues that you get from taking the spectra of this matrix. So ±4 and 6 iterations of 0. And then same thing with K. This is what the adjacency matrix looks like. Remember, it's 3 regular with 3 in each row and each column. And its spectra is ±3, and then 3 iterations of -1 and 3 iterations of +1. And then this is therefore this is its adjacency matrix spectra. Now, there's a way of calculating the adjacency matrix, a simplified way of calculating the adjacency matrix of the direct product of the graphs that involves breaking up what the adjacency matrix of each subsequent factor of the graph is and the identity matrix. And there's also a way of calculating the spectra of such a product. And the spectra is you just add up the individual spectra, and then you get all the spectra of the direct product of the graphs. So I have to rush through this now. So as a result of the previous lemma, we're able to calculate the spectra of D8 and product is or direct product of KZ4, and this is just by adding the spectra together. So that's the way you get 5, because you can add a 2 plus a 3 and a -2 and a -3 that we get from the previous spectra. And this is sort of the spectra that was used for the calculations of the rest of this paper. So, how much time do I have? 1 minute. And so much to go through, and yeah, I need to know but essentially, we had to go through some sort of equivalence relation to be able to find the central product. But the central product is essentially an equivalence relation of the direct product. So we had to come up with an equivalence relation, and equivalence relation allowed us to, by part diagram, I was going to show you, allowed us to be able to say that the spectra of the quotient graph is going to be contained in the spectra of the graph direct product of the graph. And so we were able to, using this theorem from earlier, right, that we could define its Cayley graph central product and show that it's invariant. So the Cayley graph of a central product is the central product of a Cayley graph. That was a theorem that I proved. Here we have this. And then we were able to use the fact that D8 simplifies our calculations to being able to calculate the spectra of, this is what the Cayley graph of P1 looks like when you use the Cayley graph of D8 and Z4. And then you were able to calculate its spectra, and we got it done there. And we were able to do this not only for the first iteration of the Cayley graph, but P2. This is when you take P1 and you central product it with P1, and then we can do this so on and so forth for any Pn. So Pn you get from taking Pn -1 and then central product it with P1, and then you get Pn, and we were able to show that its eigenvalues can be calculated in a rather more simple way for any n, and that was supposed to be the main part of the talk. And as I said in the beginning, how the algebraic properties of Q8 help us to simplify the calculations in the dynamical system. We're talking about quantum mechanics. Here, the combinatorial properties of D8 help us to simplify the calculations of the spectra of the graph versions of the Pauli groups, which came as a surprise to me because I thought that using D8 would simplify calculations, but it turns out that in the one case, Q8 simplified the calculations, in the other case, D8 simplified the calculations. So we don't really know much about this central product structure, but we are looking into it in terms of general graphs and stuff and working on it. And these are the references if you guys want to look into the ways in which we did our work. This was the paper that we wrote and based my thesis on. This paper I wrote for myself with regards to extending theorem, and this is the paper that the talk was based on. Very brief.
Yeah. So you connect the D8 and Q8 both the polygon, right?
Yes, yes.
Now that is the case, then there should be some relation between the D8 and Q8.
Oh no, there's definitely relations between. There's definitely relations between.
What is that?
So first of all, when you take I think it's you take their central factor, it turns out to be isomorphic to one another, and they both I think contain Z4 as subgroups. They got a lot of as a subgroup. They've got a lot of.
So when was it really started? Initially, physical quantity you started with the fermions and so.
Yes.
Now this relation between Q and the D will not be a relation going from fermions to so. So try to look at whether the duality transformation you have between fermions and so.
Yes.
Something similar should have this here between your D8 or Q8 or your Riemannian manifold, whatever the geometry, the mathematical structure you have, that also should have a similar duality relation.
Yeah.
And it will be really very interesting to find that, really explore that.
Yeah.
What is the duality?
That makes sense, Professor. But I think by the time when I decided to check with the spectral graph theory, I was so sick of quantum mechanics. I never did physics in high school or at university, and so when I did it for my PhD, I was like,
graph theory, maybe all right.
yeah. Yeah. Yes.
Okay, comes in dimensions.
Yes, yes, and I would love to see, especially since we're working with S3, I would love to see maybe like the homotopy group, the third homotopy group, and see how it works on those sorts of structures and stuff. However, we did not look at those. I think because I was just fresh out of like my PhD, and we were just specifically looking at, and I was still used to dealing with fundamental. Yeah, but looking at higher homotopy groups, what about natural?
That's why also actually this question I was also about to ask because there are more exotic particles other than pseudo fermions.
Yes.
That's what I'm looking at.
Oh, really?
Higher homotopy groups.
Like pseudo QAns and stuff. Yeah, we thought about work. We did actually busy with the paper looking at pseudo QAns and stuff. Yeah, that's what I'm saying.
That's why you're motivated.
Thanks, Yanga.